Hello everyone, I am Edoardo Maria Ponti, a postdoctoral fellow at Mila Montreal and an affiliated researcher at the University of Cambridge. Today, I would like to present my TACL paper on neural parameter factorization for zero-shot learning, which I had the pleasure to write in collaboration with Ivan Vulić, Ryan Cotterell, Marinela Parovic, Roy Reichart, and Anna Korhonen. The key intuition behind our work is that usually in natural language processing, tasks are considered in isolation, as a sort of monolith, if you want. Instead, we argue, tasks would be better characterized as the bundle of skills needed to solve them. To put it more concretely, let us start from the question, what is a possible task? At least in natural language processing. In principle, it could be any combination defined by the Cartesian product of several dimensions, downstream applications, such as dialogue and reasoning, language varieties, such as inuktitut or Thai, as well as modalities, text, speech, and so on. Nevertheless, only a tiny fraction of combinations have training data available, whereas the vast majority lacks them entirely. Thus, how can models generalize across tasks? By disentangling the skills involved in each of them and recombining them appropriately for new tasks. In this work, we assume that the space of neural parameters is structured. Hence, it can be factorized into a set of variables, one for each individual skill. Consequently, we propose a Bayesian generative model of neural parameters which are conditioned on specific combinations of skills. This allows us to perform zero-shot inference on new combinations that had not been previously observed. This idea is quite reminiscent of a classical problem, collaborative filtering. This problem is formulated as follows. Given a matrix of entries, for instance, the score that a user gave to a book, we are interested in filling in the empty cells. A common approach is factorizing the data matrix into two submatrices, one for users and one for books. Similarly, in parameter factorization, we would like to learn submatrices for languages and applications that give rise to combination-specific neural parameters. The analogy, however, stops here. The key difference being that neural parameters are latent variables, which, by definition, are not observed. Moreover, they are not identifiable, as multiple configurations can characterize the same feed-forward function. Our generative model of neural parameters can be expressed as a Bayesian graph, which succinctly summarizes the story of how the data, we think, came into existence. The task-specific parameters theta depend on a specific combination of an application T from the set uppercase T and the language L from the set uppercase L. In turn, classes Y depends on both theta and sentence input X. How then to model a distribution over parameters theta conditioned on T and L? In our case, we resort to hypernetworks. These consist in a network with separate parameterization phi, which receives T and L in input and returns mean and covariance for theta in output. In this model, performing exact Bayesian inference is complicated by the fact that the intractable integrals arise in the evidence term. Therefore, we resort to a common approximation, variational inference, which recovers a lower bound to the log evidence. This bound can be further expanded into a series of terms, which constitute the objective for our optimization. In particular, a term for the expected log likelihood requires approximation through Monte Carlo sampling. All the other terms, instead, have closed-form solutions for a suitable choice of priors. We adopt a neural architecture that is pretty standard nowadays for knowledge transfer, a multilingual encoder, specifically MBERT, whose parameters are fully shared across all applications and languages. And the linear classifier head, where parameter factorization actually takes place. Note that due to the small amount of parameters of this component, this almost does not affect time and space complexity. As for the experimental setup, we choose two applications, part-of-speech tagging and named entity recognition, which are the applications with the largest language coverage. We then select a set of 33 languages from a wide spectrum of families to ensure typological diversity. From the Cartesian product of these two sets, applications and languages, we use a subset S for training and development and a disjoint held out set U for evaluation. To put our idea to the test, we compare our model with three baselines, which do not make use of parameter factorization nor of variational inference, but are based on the same neural architecture. The first is transfer from the language in S that is closest in terms of typological feature for any given target language. The second is transfer from the language in S that has the largest dataset, usually English. The third is an ensemble prediction method where each task language combination has is given a separate classifier head. We report results for part-of-speech tagging in terms of accuracy and for named entity recognition in terms of F1 score. For both applications, the bars reflect the average among all languages in the unseen set. We find that our model significantly outperforms all baselines in both applications. In addition to performance, our experiments also investigated robustness under uncertainty. In fact, point estimates are commonly overconfident, even in high-risk settings like zero-shot transfer to resource poor or typologically distant languages. Bayesian inference, instead, yields smoother predictions. We use the entropy of the predictive distribution as a proxy for uncertainty and run a correlation analysis between such entropy and the performance metrics. We find a much stronger negative Pearson's correlation coefficient for parameter factorization compared to point estimate techniques with Monte Carlo dropout. This makes parameter factorization a more reliable estimator for uncertainty. To visualize these results, consider this violin plot, where languages are on the x-axis and the distribution of entropies for all data points is on the y-axis. Assyrian Neo-Aramaic, whose code is AII, has among the highest entropy values. Correspondingly, it also features the lowest scores in the two applications we considered. To wrap up, in this work, we tried to address some of the main challenges in multilingual and multitask NLP, namely data paucity and out-of-domain generalization. A possible solution is factorizing the space of neural parameters in order to disentangle the knowledge needed for each observed task and recombine it appropriately for new tasks. You can find the code for our experiment by following this link or scanning the QR code. Thank you for your attention. I'm really looking forward to meeting you, even if just virtually, at the conference.